yeah.
Okay, I'm recording now. I'm gonna pause it, but I mean, just to let you know.
So I think we can start. Who is recording the?
I am, and it's recording.
Okay, so we can start. And good morning to everyone. It's a pleasure to organize this second meeting of the LOCOMINAR cycle, and we hope to have further meetings in the next year, I think so. I don't think that in December we will have more interventions. And it's a pleasure to have here Amandine and Mark. And so I just, since they organized by themselves, I just leave the floor to them, and in order to start with this conference.
Thank you, Tiziano, for the introduction. So this is part of a two-part workshop of today on how to treat uncertainty in the project Locomotion. And we saw that we've got multiple entry points on tackling this, using the knowledge of the researchers in the consortium, using their previous knowledge on this topic. And one entry point that we're going to see in this first session will be presented by Amandine Pastor. And then we'll have a second session where we're going to look more specifically at how to treat parameter uncertainties in the project, and we'll present a proposal. So this first session is a public open session, and it's my pleasure to introduce Amandine Pastor. She's a researcher at the Faculty of Science at Lisbon University, where she currently works on the H2020 locomotion project, so the project that I referred to before, where she focuses on integrating the water and the land dynamics into the integrated assessment model. She's an agricultural engineer with a PhD in hydrology from Wageningen University in the Netherlands. And she's got extensive experience on the impact of global change on water resources and the different trade-offs between environmental flows and food security. She specializes on Earth system modeling, climate change, and ecosystem services. And in addition, she has fieldwork experience in sustainable agriculture and soil and water conservation projects in Europe and overseas. Today, she's going to present a study from 2019 entitled How Uncertainties Are Tackled in Multidisciplinary Science, a review to improve integrated assessment under global change. So with this, Amandine, floor is yours. And I ask you to please ask questions through the chat, either through the chat or afterwards through unmuting your microphones. So Amandine, please.
Thank you very much, Mark, for the introduction, and thank you for the rest of the team for organizing the LOCOMINAR, especially UNIP and EEB. So I'm going to share my screen. Okay. Everyone can see? Yeah, you can see?
Yes.
Okay, perfect. So thank you, everyone. So I'm going to talk about a study we did with some colleagues last year, from 2 colleagues from the Netherlands and 1 colleague from Portugal. It was also in a special issue for women in science. So we decided to as we were all from different fields, we decided to tackle a topic that is touching all of us now, how to handle uncertainties and actually how it is handled in general, and especially in IPCC and all the integrated assessment models. But before that, I will give you an introduction on what is uncertainty, etc., before we jump to the study. Sorry, I'm trying to remove some part of the Zoom. That is the, okay, it's in front of my screen, but never mind. So the context of the study is that, of course, you all know in 2016, we achieved the Paris Agreement, where it was agreed that the temperature should be below, the target should be below 2 degrees above pre-industrial levels, and we should pursue efforts to be below 1.5 degrees. So this was a good achievement. However, it was raised that there was a lack of uncertainty analysis in many integrated assessment studies. And there was this paper from Wurzel and Knutti in Nature Geoscience, where they were describing this lack of uncertainties, and also gathering for scientists to come from all disciplines and to discuss about this and how to do it. But beside this, nothing was really done. So that's why with my colleagues, we start to look a bit further on this. But from this paper, one of the statements was that the climate change problem remains loaded with uncertainty. So observations are incomplete and maybe biased. Models do not always represent all processes, and some processes are still poorly understood. So the consequences of non-communication of or negligible uncertainty analysis in climate and integrated assessment studies lead to a reduction of climate mitigation investments. So this is a consequence for policy making and implementation of our national contribution decision. Therefore, it is important to clearly define the uncertainty and the outcome of our models, and to communicate the relevance of this uncertainty to policymakers. For that, we need to understand well what we are doing, and of course, to have a framework for that. But before that, I wanted to come back to some basic of what is a system, and because an integrated assessment model is a system. So I like to show this example of the blind man and the elephant, because the elephant represents here a system, but if you look at the system from different parts, those blind men, they only see the leg as a tree, or as a spear, or as a rope. So we often think our own partial experience represents the full truth, even though other people have different experience and truth. That to say that everything is a system, even an elephant. So we need to understand the system and how different parts connect together. So how the leg is connected to the trunk. Well, we could compare like the leg to an economic model, and the head to the environmental, for instance, module. So how they connect together, and to understand well each part. And if you can't see or experience the full system, you need to create models to put it together. And it's the only way you can know your elephant or your system. In terms of integrated assessment model, more concretely, why we are using them. They are effective tool to gain insight into the dynamics of coupled Earth systems and to link with socioeconomic components. Of course, we can assess long-term global environmental issues and informing policy making about climate change. And some application of EIM, for instance, are we can assess the cause of intended climate mitigation, but we can also evaluate the combined implementation of low carbon technologies on CO2 emissions, which is the case, for instance, in locomotion. So this is the integrated assessment model of locomotion, which is called William, which has different modules: the energy, economy, population, society, and environment. If you need more details on it, you can go to the page here, but I won't make more details about the model now. just to come back to the EIMs, there are many more integrated assessment models that exist since the 90s. We will show you in the studies. But as we said, there is still a lot of uncertainties related to the data and the processes. So what if we were in a smaller session, I would ask the audience in a more interactive way for you what means uncertainty. But in that case, maybe you have an answer, you can think quickly of it. But I will give you some definition related to it, more specifically to integrated assessment model. So uncertainty in integrated assessment model can be due to natural stochastic variability, or can be due to a lack of data or poor understanding of the study system. But we can also divide it more specifically in three categories here. The first one is technical uncertainty, which is related to computational methods and potential information bugs. Can be due to the methodology, right, to the modeling tool that we use, or it can be due to epistemological uncertainties, which is where we are going to talk today, which is more related to the parametric and structural uncertainty. So to explain, parametric uncertainty is related to the input and to the parameters of the model. So if I relate it, for instance, to a hydrological model, which is something I know more, the parametric uncertainty will be related to the climate input, for instance, or the land use data or the soil. So which kind of input and what sort, maybe there are different sources. So I can have a climate data from an institute or from another institute. So that would be the parametric uncertainty. And then there is the structural uncertainties, which is related to the model processes and the equation that describe those processes. So for instance, in the hydrological, it would be the way to represent the water balance or the evapotranspiration. We know there are different methods, like we have the Penman method, we have different methods to translate those processes. So the goal is to study different methods to see the one that represents better the process, or at least to give an option, for instance, for the user of the model, so we can play with it and what is the input, to see the outcome of this latter. And finally, yes, when we use integrated assessment model, the stacking of model can lead to error propagation. So this can also be quantified. Just something I wanted to raise, and also in my case, I have been a bit confused the last years when I had to do uncertainty analysis for my studies, and I see sometimes people are confusing between sensitivity analysis and uncertainty analysis. Sensitivity analysis is part of the uncertainty analysis because it determines the amount and the kind of change produced in the model output by a change in a model parameter. So it's very specific and it's more related to the parametric and uncertainty. While an uncertainty analysis is the assessment and the quantification of the uncertainties associated with the data, the parameters, and the model structure. So it's a bit more broad than the sensitivity analysis. Just a note on how it is done in the IPCC. Beside the epistemological uncertainties, researchers need also to agree sometimes on the result and the outcome, especially in the IPCC, especially when there is a lack of knowledge or lack of a description of the processes. So how do they do that? When they present the results, we have two axes. The y-axis is the agreement between the researcher, and the x-axis is the evidence, so which is based on the type, amount, quality, and consistency of the results and the agreement between the researcher. And this gives a confidence level, right? So the more you go to the upper right corner, the more you have an evident result to present to the international panel. But when we look also at other international assessments, such as the International Agency for Research on Cancer, they use the same framework, but they add a third dimension, which is the theory. So they also agree on the background of how it is calculated and what are the processes. So I think this could add also some consistency to, for instance, to the IPCC. But it was just a note that also it's not only about calculation, but I think we as experts, we also should discuss our results, of course, now, and how we represent our processes. Now, going to the study that we developed in 2019, where there was an update, so it's now for 2020, where we looked with my colleagues. I will present you now. We looked at studies from 1990. Well, actually, we didn't look from since 1993. We did a search in Scopus with integrated assessment, uncertainty, climate change, and land use. And we have papers that started from 1993, which was the beginning of the integrated assessment models when they were starting to be developed. We retrieved more than 300 papers, but we decided to concentrate in the last 5 years due to time and resource constraint, because we did this study in a voluntary base and because of interest. So in the end, we had about 150 papers to review. From those, we selected 67 because they all needed to have a study case, model type, input disciplines, and different specification and the uncertainty analysis. And we classified them by 6 disciplines. So climate change, energy, socioeconomic, land use, hydrology, and vegetation. We then classified them into different uncertainty analysis methods. So in red are the parametric uncertainty methods, and in blue are the structural uncertainty methods. So the first one is the sensitivity analysis, the one we discussed before. This one can be to evaluate the outcome of the model by changing the inputs. For instance, with a stochastic input with a Monte Carlo simulation. Then we have multi-scenario methods. For instance, the SSPs that they are using different input parameters for, I don't know, GDP, population, land use, etc. So giving different outputs in the same model, of course. Then we have ensemble, which are a bit a mix of both, because the climate models, they represent the processes of the climate with different processes, let's say. So in this case, they represent the structural uncertainty. But then we have different emission scenario, the RCPs, and then this is the case of the parametric uncertainties, because we give a different range of inputs of CO2 emission. And then we have the multi-models. This is more and more used lately, such that the EasyMeep or the ACMeep, where they compare is the inter-comparison model assessments. And usually it has to be based on the same input models, so you can really compare the models between each other. And then we had the last categories, because more than 20% of our studies, they had uncertainty described only in a qualitative way, which was surprising, but still we had to take it into account. So if we look a bit at the results, in terms of scale, most of our studies were at global scale, and most of them were mainly calculating parametric uncertainty, but still some were also calculating the structural uncertainty. We can look at the spatial variation. We see that North America, Europe, and Australia were most of the time also dominant in calculating parametric uncertainty, so in comparing different data inputs, probably also because in those countries there is more data produced. We are not sure of why, but we have some hypotheses. And we saw that where structural uncertainty was more calculated was in Asia. So apparently they are more complex models between each other, or it can be that in some other countries, the model are already validated, so they don't need to do the structural uncertainty anymore. So this can be another hypothesis. So as I was saying before, when we compare the different methods, we look at our results, we see that, for instance, if we start with the description, 23% of our studies only had a description or qualitative uncertainty analysis. 23 had multi-scenario, 19 using multi-model, 24 were using sensitivity analysis, 4% were using ensemble, but in the end, most of the time, many integrated assessment models are using ensemble, and some had they didn't really describe how they did their uncertainty analysis. It was like 5%, or it was not really clear to us, or we couldn't fit it in these categories. And the way to present the uncertainty in more than 75% was through a graph, or 18% with a table, and 5% with a map. And we saw that according to the discipline, different uncertainty was more carried. So for instance, in energy, hydrology, socioeconomy, we had more parametric uncertainty, then it was dominant. While in land use change and vegetation, it was not always calculated. We cannot really explain why now, but it was surprising that we had these differences. Something that was raised as well is that the discipline where structural uncertainty was more calculated was in the energy discipline. So that was one of our findings, or maybe in the energy field processes needs, or it is a new component in the integrated assessment. So therefore there are more studies on comparing the processes. That can be an hypothesis as well, why this is done. So some conclusion on our results is that we didn't find any uniform approach to deal with uncertainty in integrated assessment model. We could just at least categorize different methods. We found that there was a lack of clarity in the communicating future projection in general in those studies. It was not always clear how uncertainty was dealt. We had to spend some time coming back to the papers. Parametric uncertainty analysis is used more often than structural uncertainty analysis. The highest use of structural uncertainty analysis was used in the energy discipline, as we just discussed. And in Europe, and yeah, in fact, we didn't see any structural uncertainty analysis in Europe, for instance, but we thought maybe that the model they have used, they are already calibrated and validated, so they didn't need to compare those model or processes, while in Asia it was predominantly used. In the socioeconomic field, we found that many times uncertainty analysis were justified with using socioeconomic pathway scenarios. And some conclusion and recommendation that we can give from this study is if we create an integrated assessment model, we should consider both kinds of uncertainty, the parametric and the structural. So we should look at the data stores, but also how do we represent the processes and how we link the model together. And in the case of William, since we are working with system dynamic, to be able to represent well the feedback, of course. In terms of parametric uncertainty analysis, one recommendation that we could read through all the papers is that we should include more stochastic analysis and risk analysis, including tipping points. But also we should create more fully harmonized data sets. I think the data is, the quality of the data is increasing day per day, also with the satellite images, which are a bit confirming sometimes the data that we have from the field. So this is quite good. But an example of why stochastic analysis can be useful is that in this study from Engstrom and Gars, they were showing that the optimal carbon tax was higher based on a stochastic approach because they consider higher risk than with a deterministic approach. So this can be one of the reasons why to use stochastic methods. In terms of structural uncertainty analysis, they can improve the representation of the processes in the model structure with calibrating and validating the model. So this step is really important, that we are able to represent the processes before we can do any projections. So this is like the fundamental step for structural uncertainty analysis. And of course, after that, we can compare with other models and other processes once our process is well represented. So lately, yes, we have seen the frequent use of multimodal assessment to increase the uncertainty analysis context. But also, we have seen that the quality of different models can be assessed based on expert elicitation and pedigree analysis. So there are some methods for this. And also the inclusion of stakeholders and experts to look at the models can be very useful, as we are doing in locomotion. Of course, in integrated assessment models, we should increase the knowledge in all disciplines and have a balanced representation of those disciplines in the models. And finally, I like this statement for Dukas and all, is we have to shift from the standalone use of integrated assessment modeling framework to truly integrative processes in which multiple actors and methods complement each other. And finally, by exploring and embracing uncertainty rather than ignoring it because we don't know how to do it or what are the standard methods, we could contribute to develop a more resilient society, give a robust solution under a wide range of potential future scenarios. So we could also improve the implementation of policies in terms of climate change impact if we communicate well our results in terms of uncertainty. So that was it for this session, and I hope you enjoyed and you have some questions.
Thank you, Amandine. I particularly like your slide number 20. I think we should keep that, like everybody who's working on this we should print it out and keep revisiting it, coming back to your conclusions and recommendations and check our own project against this. So if anybody has any questions, you can either put them up in the chat, or as we are quite few people, you can also unmute yourself, state your name, affiliation, and ask the question to Amandine directly.
So okay. Maybe it was very clear, or
yes, I think it was very clear.
Or not clear at all.
No, I found it very clear and very good introduction to like an overall view on the problem we're facing and on the challenges we're encountering. So maybe I'll start with a question from Luis. He says, "Thank you very much for the excellent presentation. What methods are used most frequently for structural uncertainty analysis, and which are feasible to use in William?"
Yes, that's a good question. I think there is not a standard way to calculate uncertainty analysis, because it can be, it's quite broad, but in principle, it can be that we should be sure that the processes are well represented. So the best way to take into account structural uncertainties is the calibration and the validation process. So once we can prove that our model can represent the historical data, we can prove to the rest of the scientific community that our model is working. So I think that's the first phase. Then once the model is working, we can compare it. We can compare, for instance, taking different way to represent, well, I was taking this example for hydrological model. If we take different methods to represent evapotranspiration, and we compare it in the model outcome, this is a type of structural uncertainty. So this is not a specific method, but I think the calibration, validation, and then comparing different methods that represent the processes are the basic for that. Not sure.
So maybe in this answer, just to clarify, so, well, you tell me if my interpretation is correct, but you say if you're calibrating a model based on historical data, then you have, as what you said, you do the calibration. So you test you compare the simulated values with your data, with the observations, and you try and find a model that best represents the structure you find in the observations.
Right.
So the idea there is, if you find the perfect model, so that the one that really fits well to your data and basically just leaves you with white noise in the residuals, then all you're left with really is the parametric uncertainty, which is the mapping of this white noise to the uncertain parameters, or to the estimated parameters with their uncertainty. So in that way, you could remove structural uncertainty.
Exactly.
But there may be other cases where we have models where this is not possible to do, where your data is not good enough, or where you're working from a different context. So maybe I take, I see Tiziano has a question you would like to pose directly. Maybe you want to do that?
Yeah. Thanks, Amandine, for this nice presentation to give us an overview of this issue that is really important in integrated assessment models. And I have a couple of questions. First of all, what does it mean precisely, structural uncertainty? Because, I mean, from an economist, if I think on the structure of the model, I can think on also on the theory and the, let's say, ideology behind the model. So if I think on a computable general equilibrium model against a system dynamic model or different type of approach, they can generate very different results. So from my point of view, the structure of the model is the theory that is behind the model. So how we can compare models that are based on very different theory and let's say ideological approaches that have political also consequences. And second, if from this kind of study, from your study, is how if it is possible to find a balance between the complexity of the model and the uncertainty that it can generate. Because of course, if we want to have a very realistic model, we have to increase the complexity of the model, but it can generate a lot of uncertainty. So if we can find a balance between the two.
Okay, thanks, Tiziano, for your question. I think for the first question related to the economy, this is something I haven't thought, because I was thinking more in my case when I had to do uncertainty analysis for hydrological model, where we compare the output when we represent different very different physical processes, which is the water balance or the evapotranspiration, with methods that are well known in the literature. And we just wanted to compare what is the difference when we represent that at global scale. In terms of processes for theory that are behind the economy, this is a bit more challenging, I would say, because as you say, the theory has a political driven approach, but it is always interested, I would say, to when we create a model, to introduce this other theory, and why we have this approach, what would be how our result would be divergent compared to with this theory. I think it's always important to not to hide that there are other theories, and that they are also validate for other researchers, and why we use this theory. I think in this case might be quantitative if we really want to represent the other theory, but it also can be a qualitative expression of why we use this theory compared to another one. And as they did in some of the studies, they have a qualitative approach of describing the uncertainties. And if you have the time, yes, to compare both of the theory, but this case, it's a whole, I guess, economic model that is structured in a different way. Concerning your second question, yes, I think we can go back to the elephant, to this question in terms of the complexity. When we have, I think each part of the system, if they are well represented, they can be linked together. Then what is important is the link that we create between the two components. And this has to be done very carefully. And I think we all know that, and that's why we are really careful now with creating our module in locomotion, and first testing if our model is working before we link to another part. And I think this is the tricky part, is when we start having discussion between work packages, is we need to agree on how these components are linked. For instance, for us, it will be the hydropower, the water balance with the energy module, and we need to have this discussion. First, that we are sure we represent well the system, and then how to link it. And I think we don't have to be agree of the complexity once our module is functioning, and why we know that the link that we are creating is well done. But of course, we can have some error in the data source that we cannot do anything, but we have to take it into account. And that's why we can do a stochastic uncertainty analysis. Then we can see the propagation of the error through all the model. And of course it can increase the error, but I think linking this model, the aim is to answer very important question at the political level in terms of climate change impact. So we need to put our effort on that. And of course, the model can be a bit complex, but I think if we do it this way and very carefully, it works. And I mean, since the 90s, I think we have proved that many models are functioning and they are based on very strong theory. So not sure that answers your question, or if someone wants to comment on this.
I think what Tiziano was alluding to in his first question, I think that is more going to be one of the main challenges. And it is so interesting because as you're coming from the hydrology perspective, and you are pulling your examples from the domain of hydrology, as I would be doing the same from water engineering. And then we talk with an economist, and you suddenly realize, well, you have normative decisions in the choice of a model. And so you're suddenly confronted with from our perspective, with a totally different context.
Right.
And I think this is where we probably have to put in quite a lot of effort in what you alluded to, the communication between across the different modules. And I think that is where we have potential to do some interesting work on in the project.
Yeah, I think, for instance, well, it's not economy, but more in the social module, but it can be part of the economies, the way to represent, for instance, population projection. We know that FAO and UN, they have different way to project population. Just to compare these two ways to represent the process of population projection can be a part of the structural uncertainty analysis. As a simple example. So maybe in economy, you have also different way to represent projection, or but yes, probably they are coming back to some political theory, and yeah, then
of course, maybe the easiest answer to that is, well, if you have 5 different theories, just test them all, like, you know, when you said like with a multi-model. So just use all 5 and see the differences that come out in the results. So we have a question from Tommaso related to, well,
Mark?
Yes, you want to ask?
Yes, perhaps
okay,
it's better that, yes, because I was writing down the discussion went further. So my question, I can say it better than what I wrote. First of all, is there consensus about what sensitivity analysis is and what uncertainty analysis is? Because sometimes I read something about the sensitivity analysis which is interpreted in different ways. Some people focus on input, only on reliability of data. In your presentation, it was a bit more. Moreover, is there a difference between sensitivity analysis and uncertainty analysis in the methods that you use? For instance, in my view, I think sensitivity analysis more that we can apply stochastic procedures to sensitivity analysis. Just I suppose I have uncertainty in the data, and then I can use stochastic methods to do it. While for uncertainty analysis, if I have to also to check about theories, about if I build about comparing competing theories, that's not very much a matter of randomly testing different models, but rather comparing different results from different models, in a sense. And so I think maybe I'm wrong, but to structural the structure of the model, to test the structure of the model, I think it's different from sensitivity analysis. So this is the second question, and the third is a plea. So that's I think that our model, like all models, are more tools for thought rather than a kind of prediction, and it's always dangerous to interpret the models as predictions, because history is the future is always different from history. So as it is important communicating uncertainties, just because of just for communicating that models are models, so are tools to learn about trade-offs and so on. So, but that is rather clear. But I always like to insist on this, that we don't produce predictions. We produce alternative scenarios. This is just a general plea. Thank you very much for your presentation, Amandine.
Thank you, Thomas, for those questions. I think I mixed a bit the first and the second question, but it was about the consensus about sensitivity analysis and uncertainty analysis. I agree with you, and I think in the literature often uncertainty analyses are only treated with a sensitivity analysis, so with a stochastic approach of comparing the data source and the input, but not only comparing the input, but especially what is the outcome of using a stochastic approach on the outcome. So this gives a range of uncertainty in terms of parametric uncertainty. You can also use parametric swaps, and there are different ways to do a sensitivity analysis. While uncertainty analysis, for us, what we found from the literature, because we also found different interpretation and different definition for some of them, but in most of them, what we can conclude is the sensitivity analysis is part of the uncertainty analysis. So of course, this is about testing the data and the parameters, so the parametric uncertainty, and about testing the model structure. Yes, I agree with you that we are not doing prediction, and I think in none of my presentation the word prediction appears. I always speak about projection and scenario. So in this sense, we agree. But for instance, as a hydrological model again, we need to represent the water balance. I mean, at least from the past, because if we cannot represent the runoff from one country in the past 5 years, we are not able to represent the water runoff in the next 5 years if there is climate change. So there are some processes that we really need to be precise. Maybe others are a bit more difficult, but in the physical world, I would say that the calibration process is really important. Even if with different scenario, then you would have different outcome, and this is the goal, no? But at least that you can represent the past. It doesn't mean that the past will look like the future, but if you have a business as usual trend, that you can at least project with a different range, of course, because you always have different uncertainty in the source of the data. But this is a bit my feeling. Then it depends on the theory you have to defend. So we go back to this example of Tiziano with some theory on the economy, which are a bit, which are less based on physical processes that are well known, for instance, in the biophysical world. But while a theory in economy for us is a bit more abstract. So as Mark say, in this case, yeah, compare the 5 theory if you can. And if I think that's why we saw also in many studies that the structural uncertainty is not covered, because it was covered in previous studies. So their model was proven to be functioning well. So the scientists believe that this model is working. So then they just test the parametric uncertainty and testing different stochastic approach. So a bit like Mark resumed well the presentation is, while you get removed of your structural uncertainty that the processes are well represented, let's say, you go with the parametric uncertainties. And this is mainly what we are presented to policymakers. We are not, when we present our results, we are not really doubting of our theory or how we represent the processes of how to represent water balance, because we know how it works. But the more doubt is more coming from the sources of the input and the climate data we get for climate change. And so I think this is where we have to give a range.
Thank you, Amandine. We have another question from Andre. I don't know if you would like to ask it directly. If not, I can read it. Thanks for the presentation, Amandine. Would you say that some modeling areas, for example, economy, land use, environment, are more fit for structural uncertainty analysis than others?
Well, this is a bit similar to the question.
Relates to what you've explained.
It's all related, but I think when a field like hydrology that is studied since maybe centuries, we have many theories that have been developed to calculate, for instance, evapotranspiration. So maybe now it exists about more than 5 methods to calculate evapotranspiration. And when I use a hydrological model, I can, we have the option to choose which method we want to use. Not necessarily because we don't trust one method more than the other, but sometimes it's because one method requires less input than the other. So for instance, in the LPG model, we used, I forgot it's not the reach, well, is one of the methods that require less input, because at a global scale, of course, we have less input than at a small scale. then using the Penman method, we would need much more data. But still, we have the choice between two methods. So in the case of the physical world, yes, we can, let's say, easily compare theory of processes. In other fields, I have to say, I don't know, it's especially in economy. This is like a word that is not completely new, but where I'm not used to compare theories, and I don't know if you're doing it. And when you test your processes to, I don't know, project GDP or, yeah. So probably when you develop the method to project GDP, you compare it to other theories, and this is important to take it into account. So in terms of climate, for instance, in the climate field, they are really more advanced than us because they are at the beginning of the chain, no? So it's to predict precipitation and temperature based on radiation, etc. It's very physical processes, and we have many data and many models and many institutes. That's why we have this inter-comparison modeling assessment, no? The EasyMIP. But even smarter than this, they use the parametric uncertainties, where they give different options for emission scenario on CO2 input. So then the climate data is changing according to the CO2 input for climate change studies. So I think the most advanced in this field are the climate scientists.
So what we maybe need is an intercomparison project for the IAM community. So that is related to Luis's question. Maybe you want to ask it directly if you want to unmute yourself.
Okay, as you mentioned, everything is quite related. I was coming back to the question of structural analysis. I am looking for the best way to do it in William. So I was thinking about that. And in that sense, do you think that the comparison of the outputs of different IAMs, obviously with the same inputs and the same scenarios, can be a way of uncertainty analysis, structural uncertainty analysis? So
yes,
maybe
exactly.
the easiest way to do it.
Yeah, so there are many studies now, like the AgMIP. So they think they copied the EasyMIP intercomparison model for climate assessment. Now there is the AgMIP, where they are comparing different EAMs. So I think inside was GlobalIAM, image, and they were comparing different land use projections based on different models. So in this case, they are using structural uncertainty analysis by comparing different EIMs. So it is already done. So you can look at this. There are some papers about the AgMIP, where it's called intercomparison model assessment. So William could be part then of those assessments.
Yeah.
And this could be our way to deal with the structural uncertainty as well, yeah.
Okay, thank you very much, Amandine. So it's 11 o'clock. I think we close here, and then we can move to the second internal session. Thank you everybody for attending, and I believe we need to close here, move to another room.
Thank you everyone for attending, and see you, part of you, in the next session.
Thank you very much, Mandine and Mark, for this nice webinar. Thank you.